The Philips X61 is the first xMATRIX transducer specifically designed for general imaging. Some of our other podcasts describe the remarkable features and clinical capabilities of the X61. I'm here to give you a look at some of the technology inside. Many customers have read or heard that the X61 has over 9,000 elements. The exact number is 9,212. I often get asked why we need so many. We need all of these elements for the three-dimensional acoustic beam forming that allows the X61 to steer and focus throughout the entire field of view. Let's first look at why. A conventional one-dimensional transducer has a fixed aperture and a fixed lens. We want to image in a single plane, but the aperture and lens provide an elevation beam pattern like this. We get good elevation focus or slice thickness over a limited range, with increased clutter and haze in the near field and far field. A 1D array can steer and focus within its single imaging plane, but it can't scan a three-dimensional field of view. It can't steer in the elevation direction. Some so-called matrix transducers provide a few rows of elements in elevation, which provides multiple elevation focal zones and better depth of field. This provides some improvement in slice thickness and focal range, but the improvement is limited by the small number of rows. Also, this type of transducer can't steer in elevation, so it's still imaging only a single plane. In an xMATRIX array, the elevation dimension is separated into elements in the same way that it is in azimuth with many rows. Having many rows with independent delay control provides the same degree of electronic control of the acoustic beam in elevation as there is in azimuth. We can focus the beam over a much larger focal length, resulting in good slice thickness everywhere. We can also use this electronic control of elevation to steer the acoustic beam throughout the entire three-dimensional field of view. This provides novel modes such as X-plane with two planes displayed simultaneously in real time, as well as 3D. xMATRIX also provides improvements compared to mechanical probes, which sweep a 1D array across the field of view. xMATRIX transducers can follow a similar acquisition sequence, but they do so electronically, allowing faster volume acquisition. Also, when we reconstruct C-planes from the volume acquisition, slice thickness in the acquisition planes becomes lateral resolution in the C-planes. The diverging beams in the near field and far field of a mechanical probe result in poor lateral resolution in the shallow and deep parts of the field of view. The xMATRIX transducer, with its uniform slice thickness, provides good C-plane resolution and much more uniform image quality at all depths. It takes thousands of active elements to provide this level of control of the acoustic beam, and all of the elements are used on every acquisition line. We don't use a subset of the array for different parts of the field of view or a sparse array distributed over the entire surface. Doing so compromises image quality by bringing in noise and clutter. With xMATRIX, the entire array is active all the time. Knowing that we want thousands of elements for superior image quality and volumetric imaging, we have to consider a wide range of challenges. This is a partial list of the factors that have to be considered. What makes it particularly challenging is that all of the factors are interrelated. If we try to optimize one, there are almost always trade-offs with others that we care about. The only way to be successful is to do an end-to-end system design from the front of the lens to the display, targeted at meeting the clinical requirements. The Philips xMATRIX solution is a technique we call microbeamforming, putting part of the beamformer in the transducer. Beamforming takes signals from different elements in the array and applies different delays before summing the signals. We have an array of elements and we want to look at a point within the field of view. Let's look at an example during receive operation. We need a curved delay profile along the face of the array with signals from elements in the center delayed more than signals from the edge. We start by dividing the array of elements into groups. There are 6 groups in this example. The colors indicate how segments of the delay curve correspond to the groups of array elements. The microbeamformer in the xMATRIX transducer applies delays to elements within each group and sums together the signals from elements within each group. We then send the summed group signals down the cable to the ultrasound system. The ultrasound system then applies additional delays between groups and sums the resulting signals together. This is the optimal system partitioning and design for the IU-22. By controlling the relative timing of the microchannels and groups, we can steer and focus the acoustic beam anywhere within the field of view. For example, to steer, we make the delay curve asymmetrical. And to move the focus with depth, we change the partitioning of the delays between the microbeamformer and the system to flatten the delay profile. Now let's take a look at the technology inside the X61 transducer. If we remove the lens, we see the diced array with 9,212 elements. If we were to remove the elements, we'd expose the microbeamformer circuits underneath. In the X61, there are over 8 million electronic devices that provide 9,212 microchannels, one for each element. The microchannel for each element sits directly underneath the element. And if we look down into any one of those microchannels, we find a complete ultrasound channel, a high voltage transmitter, a receive amplifier, time delay circuits, and a pad that provides electrical connection to the element above the microchannel. Now let's look at a microchannel from a different perspective. If we look from the side, at the bottom we'd see the microbeamformer circuits. On top of each microchannel is the interconnect to its sensor element, and on top of that we have the pure wave sensor elements with acoustic amplification. This structure is replicated for each of the thousands of elements and microchannels in the 2D xMATRIX transducer. So the advanced microbeamformer technology in the third generation X61 xMATRIX transducer brings unique capabilities to ultrasound to support clinical solutions. Uniform slice thickness reduces clutter and improves image quality throughout the entire field of view, even when looking at a standard 2D image. Live X-plane allows viewing of two live images simultaneously with high frame rates and control of the location of the imaging planes within the field of view. Live 3D allows imaging of an entire volume with electronic steering and focusing throughout the entire field of view. We also have MPR views with A, B, and C planes as well as 3D with image quality that's far better than a mechanical transducer, especially in the C planes. The slice thickness control means that we can look at any plane within the volume with great image quality. Developing the X61 was challenging and fun, but it's really all about providing clinical solutions. To learn more about how physicians are using the X61 in their clinical practice, please review our other podcasts.